Hey everybody, my name is Kelvin and welcome back to episode 14 of my Learn Python series. We've reached the point in the course where we can start moving beyond just fundamental Python syntax and begin looking at some of the concepts that show up in computer science courses, algorithms, and more advanced programming problems. One of the first of those concepts is called recursion. Recursion can initially feel unusual because idea behind it is that we're going to allow a function to call itself while that function is already running. There's not any kind of special recursion keyword, or there's not really that much new syntax to learn here, because everything we're going to use is just built from the functions, parameters, conditionals, all of which we've already worked with. However, the difficult part here is developing a good mental model for what happens when a function calls itself, how Python keeps track of those calls, and how we can prevent the function from continuing forever. Like usual, we'll create our lesson 15 folder. We'll create exercise-1.py. I'm going to start with a completely normal function called countdown, which receives a number and then prints that number. And write it like def countdown. And we're going to pass in a parameter integer number, and it's simply going to just print that number for us right now. And we can call it just how we've always called our function. We pass in 5 into the function called countdown. If we run this program, we know that it's going to give us 5 because the function just receives 5, prints it, and then finishes. However, here, what I actually want is for one call to this function to produce a complete countdown. For example, if I give the function 5, I'm going to want it to print 5, then 4, and 3, and 2, and 1, and continuing eventually until it reaches 0. We already know one way that we could produce that result using what we've learned so far, which would be to call the function repeatedly ourselves. So we could do something like countdown 4, countdown 3, countdown 2, and countdown 1. And this series of function calls is going to give us what we want for this exact scenario. Run this, we'll get 5, 4, 3, 2, 1. Now, the viewer can obviously see that there's an obvious limitation for what we've written down, because the countdown function actually still does not actually know how to continue counting down. We're manually deciding what the next number should be, and then manually creating every function call outside of that specific function. That would become a problem very quickly if I wanted to count down from something much larger, because I obviously would not want to write hundreds of individual calls just to produce a simple countdown. What I really want to do here, then, is to call countdown 5 once, and then have that one call continue that process. The useful observation to take away from here is that once the function has printed 5, the remaining problem is simply counting down from 4, and once it has printed 4, the remaining problem becomes counting down from 3, and so on and so on. The work that remains is always the same kind of problem that we originally started with, except the number becomes slightly smaller each time, and that will be the intuition that will be behind recursion. Here, I'm going to remove these repeated calls and add another call inside the function itself. Comment out count 5. And here, we're going to do count down number minus 1. And the important change here is the call to count down number minus 1. We're currently inside the countdown function, and from inside that function, we're going to be calling countdown again. A recursive function calls itself as part of solving a problem, usually by giving the new function call a smaller or simpler version of whatever the current call is working on. We don't actually want to call this function yet because this version of the function has a major problem, and seeing that problem will introduce one of the most important parts of recursion. Suppose we call countdown 5. The first call will receive the integer 5 and print it, and then number minus 1 will give us 4, so the function call creates another call to count down with 4. The new function call begins from the top of the same function, except its value number is now 4. It prints 4 and creates another call with 3, which prints 3 and creates another call with 2, and the process continues until we eventually reach 0. And so far, that sounds exactly like the behavior we wanted. However, think about it. The problem appears after 0 because our function currently has no idea that 0 is supposed to be the end of the countdown. The call with 0 will print 0, subtract 1 again, and create another call with a -1, which will create another call with -2, and so on and so forth. For fun, we can just call it and see what happens. And you can see that we get a recursion error. Now, how do we solve this? The condition that stops the recursive process is called a base case. And for a countdown, the natural base case is when that number reaches 0. We can add that condition at the beginning of the function. So right before our recursive call, we can add in a simple condition. If number is equal to 0, then we're going to print 0, and then we'll just return. Now, when I run the program, the countdown stops correctly once it reaches 0. When number becomes 0, we print 0 and then return from the function, which means Python does not continue down to the recursive call underneath it. Because of that return, the call with 0 never creates another call with -1. Everything that happens when we have not reached the base case is known as the recursive case. In our example, the function prints the current number and then creates another call with 1 less than the current value. The base case and recursive case have to work together because having a stopping condition somewhere in the function is not enough if the recursive call never actually reaches it. Our base case is 0, and subtracting 1 from the number each time means that a positive starting value will always reach 0. If we accidentally added 1 instead, then starting from 5 would move us from 6 to 7 to 8 and farther away from the base case with every call. So the recursion would still fail even though a base case technically existed in the function. And the idea to keep in mind here is that the base case gives the recursion somewhere to stop. The recursive case needs to make the current problem smaller in a way that eventually reaches that stopping point. There's another detail that is important when recursion is new to you, because it can look like Python is simply just changing the value of number from 5 to 4 to 3 inside one function call. And that's not what's happening. Every time countdown calls itself, Python creates another function call, and that new call has its own value for the number parameter. Let's add a print statement right here. Number. When this program begins, Python creates a call to countdown where number is equal to 5. That call prints 5 and then creates another call where number is 4. The original call with 5 has not disappeared, and it's still an active function call, but it's waiting for the call with 4 to finish before it can finish itself. The call with 4 then creates another call with 3, and the call with 3 creates another call with 2. And so on until we reach 0. So several calls to the same function exist at the same time, each with its own value for number. Python needs some way to remember these unfinished function calls and where each one should continue when the newer function call finishes, and it does that using something called the call stack. We've actually been relying on the call stack throughout the course whenever one function calls another function, but recursion makes it much easier to notice because several calls to exactly the same function can all be active at the same time. Let's add one message before the recursive call countdown number -1 and another message after it. So here we can print something like going down. And we'll have something here. Have a print statement that will tell us returning from blank number. Let's run this function and see what we get. There was a bug here where we had 0 here. Fixed it. Let's remove extra print statements. All this. When we run this version here, the first part of the output tells us that we're going to go down from 5 to 4 to 3 and 2 to 1. And then we return from 1 to 2 to 3 to 4 and to 5. The call with 1 here waits for the call with 0. And 0 finally reaches the base case and returns without creating another recursive call. Once that happens, Python goes back to the function call that was waiting immediately before it, which was the call where number was 1. and the call continues on the line immediately after the recursive call, which is why we see the message saying that we are returning from 1. After that call finishes, Python goes back to the call where number was 2 and continues from the same place and prints that it is returning from 2. Eventually, Python makes its way back to the original call with 5. The process here of working back through the waiting function calls is commonly called unwinding the recursion. The recursive calls build up as we move toward the base case, and once the base case is reached, Python can begin returning through those calls in the opposite order. Let's do another example. Our new example, 14-2.py. And here, what we're going to do is apply recursion to a string. I want to apply the same ideas to a fresh problem, and I'm going to move through this one a little bit more quickly because the recursive structure should already look familiar to you. I have this string hello, and I want to create a function that reverses it. I'll begin with a normal function called reverse_text, and for the moment, I'll simply return the string provided. Have parameter text, and all it will do is simply variable. Have it print text. If we run this, we know we're just going to get hello back because we have not actually changed anything yet. To turn this into a recursive problem, I want to think about what part of the string1 function call can handle and what smaller version of the problem can be given to another function call. If our string is hello, the first character is h, while everything after that character is ELLO. If I could somehow reverse ELLO first, I could place the h at the end of the reverse result and get the correct reverse version of the entire string. The remaining task, reversing ELLO, is the same problem that reverse text is supposed to solve, except the string is now shorter. That means we can make a recursive call using everything after the first character. Let's update our function. Here, we're going to have the recursive call reverse text, and we'll take text plus letter. Here we cut off ELLO and then add the first letter H to the end of it. Just like our countdown example here, this version can't work yet because we have not given the recursion a base case. Once the string becomes empty, we need the function to stop making additional calls. Let's see this in action before we do anything. And we can see maximum recursion depth exceeded. Let's add the base case condition then to prevent this error. If text is equal to an empty string, we'll just simply return empty string. And that's going to be the most basic version of the problem. When I run this version here, the result is going to be OLLEH. We can verify that. OLLEH. Note that the base case here isn't 0 like the problem before. The base case occurs when text is an empty string because once there are no characters left, there is nothing else that needs to be reversed. The function here can simply return another empty string without making an additional recursive call. That's recursion. Recursion is going to become increasingly useful as we move into problems where a larger task can naturally be divided into smaller versions of itself, and some of those applications will look quite different from the countdown and string examples we work with today. Here, what matters at this exact stage is just becoming comfortable seeing a function call itself and recognizing that Python is still following the same function behavior we have already been using through the course. As we continue into more intermediate computer science concepts, the way of breaking a problem into smaller pieces will start connecting to algorithms and data structures, where recursion becomes a very natural tool to have available. As always, we'll commit our changes to our GitHub repository. Git add, commit, and we'll just have our commit message be lesson 14 version. Then we'll push the repository. There we go. Thanks for watching, and I'll see you guys in episode 15 of my Learn Python series.